Hello, everybody. My name is Sebastian Skordos. This is my group. Chris Otto.
David McCabe.
We will be presenting on a little change of pace for you guys. This will be CO2 flooding. And hopefully when you leave this class, you'll know a little bit more than when you came in. Okay, so brief overview of our presentation. We're going to start with a little bit of just an introduction to enhanced oil recovery. Why are we looking at these methods? Why does this method make sense as an EOR method? And just a brief description of a few other methods, nothing in detail. We're going to move on to industry activity, show why this is prevalent nowadays and why it's worthwhile to look into this. We're going to go through the design of the projects, the screening that goes into the design. We're going to have a little discussion, and then we're going to look at our case studies and see how these are being implemented in the industry today. So we're going to start off with when do you apply an enhanced oil recovery method. This is important because if you're looking at an enhanced oil recovery method, you want to know why you're looking at this. So your drive mechanisms due to primary and secondary recoveries are exhausted, so you no longer have the initial recovery from just the reservoir fluids increasing the pressure, allowing for that natural pressure drop. You no longer have water flooding or produced reservoir fluid flooding that allows you to maintain that pressure, so you're looking for another method that will allow you to get more production. This is important because primary and secondary can leave a great amount of oil in the reservoir, and sometimes an EOR is able to recover up to 90% of that oil, where primary and secondary may only get about 50%. So just like any other method in business, you're going to be deciding based on economics. So if you're going to be applying an EOR method, you have to decide, is the production I'm getting offset by the costs I need to apply to get this production? So obviously, the production is going to be on a well-by-well, case-by-case basis. Every reservoir is slightly different. Every method is not going to be applicable for every case. You have to take it case by case and see what happens. Okay, so just a few types. You have thermal and non-thermal EOR. Thermal EOR, as they so lovely described, is increasing the heat to increase your recovery, decrease the viscosity. Your gas injection on the side, chemical injection, and microbacterial injection, all are used to change the composition of the oil downhole, and that'll allow you to decrease mobility ratios, increase mobility, allow for easier flow downhole.
So now we're going to look at some industry activity. CO2 miscible injection basically took off in the 70s, and the first major projects came in the 80s. So the SACROC unit was in West Texas, and that was pretty much the first big CO2 flood, and that was funded by Exxon, Chevron, and a few other operators. So they saw their OOIP production increase by 10%. So that kind of sent a shockwave into the industry, letting them know that CO2 miscible injection might be worth it for other companies. There have been major miscible CO2 floods in the states that are listed here: Texas, Colorado, New Mexico, Mississippi, Oklahoma, and Wyoming. However, Texas has most of the CO2 floods, and that is because of the type of oil they have. They have a light oil out there, and they have high enough reservoir fracture pressures to tolerate CO2 injection. And so on the right, we can see the breakdown of the different recovery methods versus time, and we can see that from the 80s, CO2 injection has increased their share amongst the different types, and that's going to continue to grow into the future if you look at forecasts, maybe based on some potential carbon sequestration subsidies.
Okay, so now we'll go into the design and implementation of CO2 projects. So a project design is going to take a great amount of time. This particular project that we're looking at in Saudi Arabia was scanning their reservoirs and determining what wells would be a candidate for CO2 flooding. So they started by scanning all of their reservoirs, finding out which ones had a light oil, high fracture pressure, and other parameters that are favorable for CO2 flooding. And after they selected all their candidates, they got as much data as they could on these reservoirs and took it into more in-depth analysis in laboratories and did their studies on those, got as many parameters as they could. The more data, the better. And then after they took all of these, scanned them out, found the good reservoirs to qualify, they were able to make a pilot design based on this data and take that pilot design, scale it down on a reservoir by reservoir basis. This allows them to minimize the amount of capital they're spending on their project, allows them to get better data, apply a pilot design, evaluate that pilot design, and then maybe scale up in the future. So it's more efficient to do it this way, and it takes a lot of time, but you have a great method selected, you have your data, and you're able to select and choose which methods you need.
Now, this is the fun part. I'd like to talk to you about the screening criteria. Are you guys excited? Say yes or yes. Yes. Great. So gas injection for the light oils, I like it because it's not only self-explanatory, but it's easy to remember. Now, the processes of gas injections, their oil recoveries, operate the best under a specific situation where the gas can become miscible with the oil of the reservoir. Now, you might be wondering, what is the goals of gas injection? There's only but two in this case. So the first one is to reduces the residual oil saturation below the levels that we get through water flooding. The second one, which is my favorite, is to enhance the low coefficient displacement. After all, this is an enhanced oil recovery presentation. Next. Great. Now I'd like to present to you some examples of miscible gas injectants. Now the first one, which isn't my favorite to be honest, is nitrogen, and for the people that like chemistry, it is N2, that's the chemical formula for it. The second one, which is commonly famous across the Hall of Fame, as somebody might say, is carbon dioxide, which is CO2. Now, both of them have to be at high pressure, because the higher the pressure, the better it mixes the gases together. We are striving for miscibility where the injected CO2 behaves similar to the reservoir fluid in mixers, as I said earlier, and it increases mobility. Now, how do we know if it's miscible or non-miscible? What do we look for and what do we do? So we are looking for the minimum miscibility pressure. And there's that number again. There's two ways to determine if it's miscible or non-miscible. Now the first one is to have it examined by the laboratory through experiments that are called slim tube experiments. Or we could do another one, which I like because it's like a simple mathematical formula. That's how I see it. You just combine two things together. Now the first thing you're going to combine with the phase behavior measurement with the compositional stimulation, and that will tell us whether CO2 injection is feasible or not. Now this is the slim tube test diagram. I'd love to talk to you about it in detail, which will take about 5 to 7 minutes, but unfortunately we don't have that much time, so I'll stick to basics. So it basically, we're trying to basically simulate the reservoir to see if CO2 is miscible in oil.
Now we're going to talk about some case studies. So the first one, it also comes from West Texas. It's the San Andreas unit, means San Andreas unit. Like I said, Texas is prolific for CO2 floods, especially the Permian. So the flood started in 1983. I guess before the flood, they were on 40-acre spacing. They had drawn the wells down from primary to secondary. They had about 30% of their OIP produced. And then they infill drilled down to 20-acre spacing. And the reason they did this was The structure of their well bores, their current well bores, couldn't handle the injection pressure, which is what we're going to talk about. So they infilled down to 20-acre spacing, and the final pattern was a 9-spot pattern. So here's the field off to the right. You can see it, and you can see this is an older picture of it. So as they were producing with the CO2 flood, they were continuing to infill drill. But you can see in the top portion the nine spot pattern. But our porosity and permeability, 9% and 20 millidarcies. And these are some other reservoir characteristics. But what we care about is the oil gravity and the oil viscosity. Remember, this is a light oil. It's important that we have a lighter oil when we're looking at miscible CO2 flooding, because we're not going to be able to make that CO2 miscible if we have with heavier oils. And then that's going to play into the pressures, which we're going to talk about. So this field's 6,700 acres, 167 patterns. The fracture pressure in this formation was 2,800 psi, and our minimum miscibility pressure, which is low, and our minimum miscibility pressure was, it ranged, they used slim tube testing, ranged from 1850 to 2350, so relatively high minimum miscibility pressure. So they chose an injection pressure of 2,000 psi, but that varied across the field, and that's just to keep it, again, in that window. So here were the results. You can see at the start in 83, they were producing about 7,800 barrels of oil per day. And then when the study commenced or ended in 03, they were producing over 14,000 barrels of oil, so significant uplift in production. They went from 30% of their OIP to 45% at the end of the study.
So I did the second case study, which was for which was by Ton and David, which was for the Eagle Ford Shale, and it was a simulation of different types of CO2 injection that they used in a model from the Eagle Ford Shale reservoir. And these simulations were to show how each different CO2 injection were to optimize the performance and the recovery of the reservoir. David. Starting it, they had to create a model for the reservoir. Because this was only testing the flood of the CO2 injection, they didn't really want to go too in depth with the reservoir model. But to do it, they did a dual porosity structured grid model, and which gave it enough information and data, but which simplified the data, but it didn't take too much time to run the simulation. The reservoir was 5,000 by 1,800 by 100 with 12,000 foot depth. And they didn't take the vertical flow into account because it was just in the CO2 injection in the lateral part of the well. In the reservoir, they decided that to use volatile oil because that was most commonly found in the shale of the Eagle Ford Reservoir, and they simplified down the basic components with N2 to CH4 being about 63% of the fluid that was still in it. Because, like I said, it was just for the injections, they still had to do a hydraulic fracture design for the shale. And instead of doing a complicated one, which a typical Eagle Ford Shale hydraulic fracture consisted of 3,000, 5,000 foot with 10 to 20 stages and 4 to 8 clusters each. They decided to just do 4,000 with 20 stages and a cluster on each. But they made the fracture length about 300 foot half length, with the hydraulic fractures being planar and having 10 millidarcy per foot at the heel of where the fractures would start, and then about 5 millidarcies per foot at the toe. With the different types of CO2 injection they used continuous CO2 injection. One thing that they did was they split it into two, and they did one with open and one with closed. And the one with the open is where they had the injector well going while the producer well was also open, and with the closed, it was the injector well was going while the producing was closed for about 1,000 days, and then they would open it. And then they also did a water alternating gas injection, which is basically what it says, where they would inject the CO2, and then at time intervals there also inject water, which would lower the CO2 injection. They also did a huff and puff, which we learned about, which was different from the other two because it only used one well that would act as the injector and the producer, and it would inject for a certain amount of time, and then it would start producing until they would start injecting again, and it would go at a cyclic rate. With the conclusion of it, because water is so hard to inject at nanodarcy permeability, a lot of companies have been using gas injections, and during the simulation it was concluded that the Huff and Puff was the most successful because they used the fact that 2 Huff and Puff wells could be used for the continuous and the WAG, and it also used less CO2 injection as a continuous close, which was the highest, and which gave you the highest recovery. And they also found out that the continuous with the open producer was the least cost effective and gave you the least production recovery.
So, in conclusion, we're looking for high GOR reservoirs with light oils on a high fracture pressure in a given formation and a low minimum miscibility pressure. There are multiple methods of CO2 injection, as Chris just talked about, and you have to vary those case by case, try them out, and see which ones work. A CO2 source, we didn't get into the economics because of time constraints, but the main deciding factor in the economics of miscible CO2 flooding is getting CO2, putting the pipelines into place that can transport them to your wellhead. So that's the main economic role. And the oil price obviously plays a role, but we found a study from 2004 that said that CO2 injection is economic down to $20 a barrel. You probably wouldn't want to implement a flood at $20 a barrel oil, but it's sustainable. With that, we have time for questions.